We live in the age of the Anthropocene. From Earthrise, we see a network of noxious megacities, from Moscow to Tokyo, each with their own hyper-dystopian industrial infrastructure, toxifying our atmosphere and waterways. Some of the concentrated urban cores demonstrate almost 100% water toxicity due to the hyperdense industrial networks being brought to our city shorelines and river deltas, as seen here in Tokyo Bay's Kawasaki ward. Samples of water taken in cities across the world show hypoxia, the complete depletion of oceanic oxygen, and eutrophication, the imbalance of water nutrients, signalled by algal and lichen blooms. This is a post-human global crisis, with our oceanic biomes becoming more poisonous every day. By using the proxy of Tokyo's eutrophic condition, the Bloom Network, an algal biopolymer research centre in the hypertoxic Tokyo Bay, proposes new symbiotic architectures, which learn from the insurgent byproducts of this toxic condition to bloom data-driven, carbon-negative architecture to bring about the end of toxicity. Insurgent natural growths and blooms, such as lichens and algae, are the primary byproduct of this eutrophicated condition, which aim to naturally sequester carbon and symbiotically detoxify the environment. By digitally reinterpreting their symbiosis and growth patterns, we can develop an understanding of how to bloom insurgent carbon-sequestering architectures for our post-anthropogenic condition. Fruticose lichen grows following dendritic branching, analysing curvature to search for new symbiotic material, whilst crustose lichen grows proportionally and additively, adding new lichen on top of carbon-spent microorganisms. Foliose lichen, however, grows recursively, with a gradient of exponential growth as more symbiotic material is used up. In natural insurgents, the human is solely an observer. However, we can begin to digitally inject data into insurgent blooms to analyse the growth and flow patterns of algal bloom in eutrophicated waters. In this initial test, the spread of toxic algae is digitally represented by analysing the colour, and therefore toxicity, of algal bloom data from NASA imagery. By altering the input data of the algal symbiote and algal toxicity, we vary the digital output of its growth. Term 1 studies pursued these ideas of a digitally regulated natural insurgence. I began to reinterpret the Japanese Kagome basket weave as a series of algal channels with carbon-sequestering symbiotic nodes at each point of woven overlap. Using a machine learning algorithm, I was able to vary this weave density, and therefore the amount of carbon sequestered by the algal woven system, based on live and historic carbon output data from Tokyo, suggesting a data-driven intervention of carbon neutralization, much like the lichen and algal blooms found in nature. These symbiotic data sculptures are extracted from the 3D machine learning algorithm and represent a carbon offset for Tokyo's municipal waste carbon output in terajoules from the years of 1998, 2005 and 2012. Initial architectural speculations proposed a culmination of Term 1 studies using digitally analysed algal flow patterns to create complex networks of fibres, which are able to pull algae passively from eutrophicated waters through cohesion tension. Structural reinforcement comes from another symbiotic agent, mycelium fungus, which works alongside the algae to bloom carbon-sequestering lichens, which can be controlled with varying Kagome weaving areas on each pavilion, allowing for a data-driven carbon-sequestering pavilion typology to bloom. Japan has one of the highest levels of water pollution, eutrophication and toxic hypoxia in the world, with many dense urban centres and heavy industrial waterfronts polluting the shoreline biomes. Tokyo Bay is a typical example of this problem, with a vast network of chemical fertilizer factories along the bay, including Kawasaki Ward and Chiba waterfront. Furthermore, as a city built on various river deltas, the underground rivers which run under Tokyo pour the harmful pollution from the city and peripheries, such as toxic waste and fertilizers, directly into the Bay Area. By digitally mapping the data of eutrophication and toxic algal bloom in Tokyo Bay using NASA data, we can observe the worsening problems with high toxicity and a dangerous shoreline biosphere. The very epicenter of this toxic condition is Odaiba Island, one of the largest islands of the network of 250,000 square kilometers of reclaimed land in the bay, with a disused peninsula at the most northerly point. This peninsula, Daiba Park, like many of the reclaimed islands throughout Tokyo Bay, sits on top of historical macroalgae farming infrastructure, which once saw humans working symbiotically with the algal blooms within the bay to regulate and harvest algal food and fuel. This infrastructure, visually represented through its iconic layout of rows of stilts, was completely erased to make way for the hyper-polluting reclaimed islands that we see in the bay today. The use of image processing of satellite imagery to remotely analyse algal concentration within the toxic waters of the island enabled the specific localising of a site on the disused Daiba Park due to its highly eutrophic condition, designated as the most in need for carbon-sequestering detoxifying architectural blooms. Learning from the layout of historic macroalgae farming infrastructure once found on the site, a structural column grid is grown. At each of these points of intersection, the algal flow within the water is digitally analysed and reconstructed on an architectural scale. A fibrous data-driven architectural language begins to bloom. Using a neural network to learn from the varying density of Japanese basket weaving, the fibrous density is analysed for areas of structure and porosity. These areas dictate the layout of internal divisions and walkways. These walkways are then placed in areas of higher structural density, and a series of rooftops define the internal spaces of the network as a series of cascading layers. The network is laid out on a series of 3 spines, public, private, and mixed, all of which serve different programmatic functions. At the center of the network is an auditorium for the client, the Japanese Algal Symposium, to use as their primary biopolymer educational space. Along the right-hand bank of the island, the private spine contains the University of Tsukuba algal biopolymer research facilities, including laboratory spaces and material fabrication. And on the opposite side of the network, the public spine hosts a biopolymer material exhibition space and algal-based food and beverage. The mixing and layout of these programs supports the symposium's aim to promote the research and education surrounding algal biopolymers, whilst the network directly uses the resultant algal bloom from the surrounding waters to supply the lab spaces with freshly bloomed algae to research and convert into carbon-negative biopolymers. The capillary system, informed by the direction of algal flow, is split into 3 closed-loop gradients. System A and B, containing euglenophyta and chlorophyta respectively, are highly photosynthetic and sequester large volumes of carbon given varying light conditions. System C, which is capable of secondary symbiotic relationship with glucose and E. coli, promotes natural bioluminescence as a wayfinding strategy throughout the vast network. Due to the reliance on instant UV light as a foundation of the photosynthetic carbon sequestration process, the density and bundling of the capillary network is informed by annual cycles of historical UV data for Tokyo Bay. This promotes a variation in the facade condition, which is constantly in flux as the digitally flowing algal network mediates the building, blending from architectural elements to carbon inputs and louvers. This variation allows for areas of greater carbon sequestration due to varying pipe conditions within the capillary system, with carbon inputs of various sizes and a varying condition of an open and closed loop system. These algal systems work on a surface area to volume ratio gradient from the largest algal bloom decks, situated on the ground of Diver Park, through to primary transportation pipes, secondary facade pipes, and tertiary algal bloom capillaries. The constant variation of the surface area to volume ratio allows for specific control over the rate of carbon sequestration and the efficiency of the detoxifying system of the network, constantly symbiotically responding to the internal requirements of the lab spaces, such as UV exposure, humidity, and temperature, which can all affect the biopolymers and their testing. An example of this symbiotic relationship between internal condition and algal bloom can be seen in the transparent algal louvers. The rate of bloom of the algae within the louver affects its opacity, and therefore its ability to absorb UV and protect the inhabitants of the building from harmful rays or from improper light conditions. The same mutually beneficial symbiosis can be observed with the density of the capillaries, which, at the optimum density, can prevent wind flow and promote the dehumidifying condensation due to rapid freshwater cooling, creating a symbiotically regulated microclimate around the building. The bioluminescent wayfinding strategy is another example of this symbiotic architectural system, promoting the reaction between E. coli and cyanobacteria in specific capillaries to biologically glow and light the network. All these variations in the facade condition allow for spaces which are constantly internally responding to the algal bloom and sequestration. When isolated from the internal volumes, the complexity of this capillary architecture is revealed. By isolating the biopolymer research cluster, we can begin to understand the integration of these systems into the larger building network, a form of infrastructural symbiosis on an architectural scale. Alongside the algae and bioluminescence, the capillaries blend into architectural features such as staircases and balustrades, as well as hosting the various MEP systems of the complex biopolymer laboratory spaces. These systems work together in a symbiotically mutually beneficial way, learning from algae to exchange heat, waste biomass, and embodied energy. Internally, these fibers become both functional and highly performative, with the digitally interpreted flow of algae channels carving out the auditorium and the lab spaces alike. Complex algal interiors respond to the external toxic condition of Tokyo Bay. In learning from the Bloom network, we can suggest ways in which our cities can become truly symbiotic, a utopian aim to mediate the needs of our urbanity with the promotion of insurgent architectural blooms which catalyse the end of toxicity. By extracting the condition of neighbouring sites, we can begin to suggest and speculate a city-scale parasitic bloom network, which recursively spreads as an architectural lichen to heal our urban cores. These urban conditions can be split into 3 subgroups. The first sees the awakening of disused carbon-rich sites, with the network blooming in response to historically embodied carbon data on the site. This would primarily see the carbon neutralising of disused mines and factories across our cities. The second would see our highly polluting and toxic transport networks reimagined as search channels in the network spread through the city, in which the density of capillaries responds to the carbon emissions from the vehicles on these routes. And finally, the third condition suggests a parasitic engulfing of our residential tower blocks to neutralise the toxic output of each resident through varying capillary conditions, which are constantly in flux, blooming around the residential units with the highest carbon output.